worse.
I know, the excuses are very, very unimpressive. I mean, sick it's been so, I got sick. It's very, very unimpressive. It's been done before, you know, I mean, but anyway, yeah, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for this class and your creation, that we can understand a little bit about it, and just help us to glorify you when we do, Lord. In your name I pray, Lord Jesus. Amen. So, you know, something slipped past me in terms of like describing properties of holomorphic functions. And so we talked about, let's recap, you know, of course, functions complex differentiable on an open set around the point, then it's be holomorphic at the point, right? And we talked about how if you have continuously differentiable and you satisfy the Cauchy-Riemann equations, then you're complex differentiable at the point, indeed holomorphic at the point, because you're satisfying that condition not just at the point but nearby it. We also had the criteria of Carr-Theodori as a way, or the Wirtinger calculus, right? We have all these ways. And then we also talked about how if the derivative is non-zero, complex derivative is non-zero, then the mapping is conformal, right? In the sense that it preserves the angles between paths that it maps. So we had that, and then we talked about how the real and imaginary components of a complex differentiable function have to separately solve Laplace's equation, right? But there's something else I could say which is really low-hanging fruit, and if you take a step back and look at how all of the different examples we have look, you'd eventually notice this, that if you look at the level curves of the real and imaginary parts, like, for example, let me just try to make this like a little bit more down to earth here. So if, you know, I have f of z equals to z, right? X plus iy, right? So you've got u of xy equals to x, right? V of xy equals to y, right? So what are the level curves of this? So if I set this equal to x naught, I set this equal to y naught, the level curves are fairly obvious, right? They're what? I don't want to spend a lot of time on this because it's really kind of boring, but here's the level curves, right? Y equals to y naught, things like that. And the, you know, over here, x equals to x naught are the vertical lines, right? And those are, well, those are orthogonal trajectories, right? Wherever they meet at a right angle. Is this just because it's z, or is this something that always happens, right? Like, let's see here. Example 2, you could do like, you know, f of z equals to z squared, right? Which is x squared minus y squared plus 2i xy. And I think we actually looked at this before. This is u, and there's a v in here, right? Put the 2 over there so I can emphasize that's the v, right? And again, if you were to look at u of xy equal to, you know, a constant, and v of xy equals to a constant, what would you get? Well, you get level curves, right? Those are so-called level curves. That's what a level curve is, you know, a solution set of a level function equal to a constant. And so if you have x squared minus y squared equals to u naught, well, those are, let me put in something here. Well, actually, fine. If we put u equal to 0, we get these, right? U equals to 0 gives me y equals to plus or minus x, right? So here's u naught equals to 0. And then otherwise, we got these guys, right? And you could work it out, like the vertically opening ones come from what? They come from u naught positive or negative, what? So the vertically open ones don't have y equals to 0, right? So the vertically opening ones are like u naught greater than 0. And these guys over here would be u less than 0, horizontally opening. If you look at that equal to a negative number, you can get x equal to, oh wait a minute. Yeah, if it's equal to a negative number, we get minus y squared equals to the negative number. So y is equal to plus or minus, oh wait a minute, other way around, isn't it? Well, anyway, you work through it. Tell you what, I'm not going to commit. You can figure it out. All right, I'm going to let you guys figure it out. Because you need to work on these things. Looking at the homework, you need to work on these things. So which one's which in terms of the hyperbolas, right? But of course, if you continue going larger values, you get, I mean, we could settle the issue if it's bugging you guys. What do you think, Shane? Which one's opening vertically, which one's opening horizontally in terms of like u naught being positive or negative?
It looks like the ones that intercept the y-axis would be the ones for u naught greater than 0. If that's what you're asking.
All right, let's try that. So for instance, x squared minus y squared equals to minus 1 or?
1.
1. All right. So then if we put y equals to 0, we get x is plus or minus 1, right? So these guys, the horizontally opening ones are the positive. The vertically opening ones are the negative. All right, there we go. I forget what I had written before, but whatever. Okay, anyway, so that's the family of curves that these are hyperbolas, and then of course the asymptotes are special cases, right? And what happens when you put v equals to these guys here? Let's look at it for a second. You're looking at 2xy equals to v naught, right? So y is equal to v naught over 2x, right? Those are that's the reciprocal function, right? Basically, and so those things look something kind of sort of like this. All right, so this would be if you had a positive v naught, and then a negative v naught's going to go over here like that. And if I did it right, these would meet what? I'm ruining this red marker, passing it through all this blue. So those are, it's an orthogonal, these are orthogonal trajectories, right? Every time they meet, anywhere they intersect at right angles if I graphed it right. This is not an accident. Why is this always happening? Why is it that the u and v level curves are perpendicular? So how do you understand this in terms of calculus 3? Very easy. Remember that u of xy equals to u naught has gradient of u perpendicular to the level curve, right? And likewise, if we put v of xy equals to v naught, look at that solution set that has the gradient of v perpendicular to, the curve, right? So if I draw, if this is u equals to u naught, right, then this thing is what the gradient of u field looks like, right? And if I draw v equals to v naught like this, that's my v naught level curve, then the, I'll draw it down just because it's my picture's getting busy. But, it's perpendicular to the curve, right? But that's something like the gradient of v. I mean, I don't know which side it is on without the details, right? But it points perpendicular to the curve, right? And the question then is, what if you look at a point of intersection, right? Like right here maybe. We could compare, right? We could compare the gradient of v and the gradient of u. And what would we find out? What do you think the angle is going to be between those? So let's work it out. How do you do that? Gradient of u, dot product, right? The gradient of v. What is that? So you got yourself ux, uy, dot product vx, vy, right? And so that is ux, vx plus uy, vy. But if this is not just any old pair of functions, it's the real and imaginary parts of a complex differentiable map, then what can you tell me? These satisfy the what? Cauchy-Riemann equations, right. So we can trade what? Which one do you want to keep, the u or the v? Keep the v? Okay, so ux is equal to vy, and uy is minus vx. So I'm going to trade my u's for v's. Ux is vy. So I got myself a vy, vx, minus vx, vy. Hey, what do you know? 0. And this analysis works provided what? Provided that the gradient of u and the gradient of v are non-zero, which will be the case when? Well, it'll be the case when the complex derivative is non-zero, all right? There's another way we could understand this just in terms of like conformality that I just thought of. It's kind of a weird argument, but so you can also think of it in terms of just the fact that, like, if I have a complex function that's orthonormal, I mean that's conformal, it's mapping. No, I don't have it. Never mind. I thought I had a different argument, but I can't put it in the words. Yeah.
So
this is a perfectly good one. Yeah.
On the homework,
Yeah.
we were solving for
Yeah.
and what my calculations seem to lead to is that a lot of them had arbitrary constants.
Oh yeah, we can always add an arbitrary constant to v. Yeah.
But it's like what you're doing here. You know, any of those level curves are still orthogonal trajectories, so it still works.
Oh right, yeah, because adding a constant just shifts you to a different level curve, right? It doesn't the geometry, like we're thinking about a whole family of curves, right? So like if your freedom to add a constant to the harmonic conjugate just kind of reindexes the family. It's, yeah, that's funny. I hadn't thought of it that way. Interesting. So I was supposed to talk about inverse functions, right? So let's do that. So so I already talked about the inverse function theorem, right? I already talked about that. And but now I want to just talk to you about how we can actually calculate the derivatives of some inverse functions, right? And also I want to talk some about the issue of branch cuts, because there's some subtle things there. And I do think that the book is really good. Like, you should definitely read chapter 3 and try to appreciate what he's doing there. It's very helpful. All right, so anyway, inverse functions. So in a nutshell, if if you're looking at f of z with f prime of z not equals to 0, f prime of z not equal to 0, then if you're looking to solve w equals to f of z has solution z equals to g of w, where f of g of w is equal to w, and g of f of z is equal to z. I mean, they're inverse functions, all right? And to be clear, this is for z sufficiently close to z naught. So the inverse function theorem is a local theorem. We know we can't have an inverse globally, because if the function's not one-to-one, we can't find an inverse, right? And we know lots of functions are not one-to-one, right? You got a homework problem where you're asked to show 4 different common functions have a period, right? That they map back where they were again. So like you find the period of sine, of tangent, I think of cosh maybe. So a lot of our elementary functions are periodic, and if they're periodic, that means that they're mapping, the same inputs, many different inputs to the same output, right? So they're not one-to-one. So the concept of inverse has to be local. All right, so let's actually talk about how to actually calculate this. So let's see here, example 3. So I think your homework had, if I remember right, I'm trying not to work your homework problem. I've had a problem with that this semester. Right? It's definitely a problem. Not for you though. Let's see here. Where's my problem? Where was that thing? So, just trying to make sure I don't. I think I asked you guys to do problem. What was it? Oh man. I was just looking at it before class. No, I can't find it. Do. Do you guys remember? It was like find the derivative of inverse cosh or inverse sinh. Remember which one it was?
I think that might be 37 or 38.
Yeah, sadly I don't have that in front of me.
It might be like 3 biggest 35.
Which problem is it in the book?
Oh yeah, it's 3.214.
3.2 number 14? That sounds right. I gotta make sure not to do that one. Oh, that's the periodic problem. Not that.
3.311?
I don't mind doing that one. That one's easy. What's 3 point what?
Oh wait, derivative of inverse hyperbolic sinh.
Okay, so I should do cosh then. All right, so let us look at W. All right, so I want to look at W equals to inverse hyperbolic cosine of z. All right, so I'm trying to find the derivative of this. Okay? So the first thing I do is I take cosh of both sides. Cosh of W is equal to z. Cosh of cosh inverse of z, which is z, right? Now what is cosh? Well, it is 1/2 e to the w plus e to the minus w is equal to z. Multiply by 2 because we hate fractions. E to the w, I'm sorry, we strongly dislike fractions. What was I saying? I'm sorry. This is liberty. Although we are supposed to hate sin. I don't know. Fractions are sinful. Yeah, I guess not, so probably. Decimals are. Okay, so how do you solve this for W? Oh, we should just take a logarithm, right? But that's troublesome because you don't have one exponential, right? You've got 2, and log of a sum is nothing nice, right? If you think log of a sum is something, then you're probably a freshman and you probably need to be corrected. There's spots. How about this? Multiply this by e to the w. What happens? We get e to the w squared plus 1 equals 2z e to the w. Great. Hey, well that's starting to look like something. This looks like an e to the w squared minus 2z e to the w plus 1 equal to a 0, right? And then, well, complete the square. So this is e to the w minus z quantity squared plus z squared plus 1 equal to 0. My bad. Not plus z squared, but what? So if you FOIL out the square I just wrote, right? If you multiply this out, what do you get? You get back e to the w squared minus this term, right? Plus a z squared. So to be fair, I don't add z squared here. I do what? I have to subtract it, right? But that's just completing the square. And then I can isolate the square. So I got myself an e to the w minus z quantity squared is equal to z squared minus 1. Lo and behold, e to the w minus z has to be equal to z squared minus 1 to the 1/2. Now here I am using the notation of equality for element of, that is the set of square roots, technically. If you'd like me to write this less, I mean, I could write it this way instead, you know. this is plus or minus the principal square root of z squared minus 1, yeah? We could do that. Yeah. And if we did that, then we could solve for e to the w. We got ourselves e to the w is equal to z plus or minus the square root of z squared minus 1. All right, great. And our goal here was to solve for w, by the way. So solve for w. I get w is little log of z plus or minus the square root of z squared minus 1. So, yep.
Can you remind me again why that's a little log and not a natural log?
Because the exponential is not single valued, like it allows this 2 pi periodicity times I. So if I have e to the w1 equals to e to the w2, all I can tell is that, you know, w1 is equal to like w2 plus 2 pi I times k. Like that's all I can get. So we worked out in a previous homework problem that if we have e to the w equals to Pac-Man, then w has to be an element of the little log of Pac-Man. So capital log is one solution, but there are in fact infinitely many solutions. Yeah. And all right, so to summarize, then we've found this lovely formula that shows you something, which is that the inverse hyperbolic cosine is not one function. In fact, it's a multiply valued function, and you could choose any, you know, you got many choices here, right? In terms of which logarithm you use, but also whether or not you choose, you know, the positive or, I mean, for that matter, you could also choose a different branch of the square root function there as well. So you have both of those options in play here. Which choice you want to make for the log and for the square root depends on the application. But of course, as a starting point, we could just say, so like, I think what the book does is it like will capitalize Cauchy inverse, and this will be like the principal inverse hyperbolic cosine, and that will be defined by the principal log of z plus the principal square root of z squared minus 1. And there you go. Now this is unambiguous. It's not a multiply valued function. This is a single, you know, choice of the, that's a choice of the multiply valued function above. Right? Now that still hasn't answered the question, how do you differentiate it? Yeah. So actually the question of how to find the derivative of it is much easier. So this is just an identity I'm working out for you, but this is what's intended, I believe, in that homework problem, is to work out the corresponding identity for inverse, for sinh. Almost the same calculation goes through. Like if I pretty much showed you how to do that homework problem, truth be told, right? Because the only difference between Cauchy and sinh, you go through this whole same argument, is just instead of having a plus here, you've got a minus, right? And actually, if you think about it, this also, the same calculation will show you why the book has the identities it does for like inverse sine and inverse cosine, all right? Because it's the same calculation, it's just instead of having w, you've got iw and minus iw for like cosine. Or with the sinh, there's a division by 2i and there's an I. But otherwise, the algebra is pretty much the same. All right, so let's figure out what the actual derivative is. So if you don't mind, I will do that over here. Okay, so let's see here. Going back to before we got into all this, we've got, and this may not be the idea, like the book may actually have in mind that we differentiate this to derive the formula for the derivative, but I say we go back and do it an easier way. which is simply this. If you've got cosh of w equals to z, then we can differentiate. Using the inverse function theorem, the derivative exists, right? So that means that we can apply the chain rule here. What's the derivative of cosh? Well, we know, I'll write it out here. So ddz of cosh w equals to dz dz, right? And I'm within my rights because, this is the derivative of cosh non-zero. Well, let me go back to the, well, anyway, let's think about that in a second here. I was thinking about, have I met the condition I need for the inverse function theorem to hold? Well, let's think about it. So this is 1, right? The derivative of cosh is sinh. We got sinh of w, dw dz, which is what we're after, right? So solve for dw dz. Apparently we got 1 over sinh w, but what is sinh w? Well, I will tell you. So you can prove that cosh squared w minus sinh squared w is equal to 1. Right? This is an identity which is true for all w. And you could easily prove that by looking at this as a function of w, right? Differentiate with respect to w, show the derivative is 0, check that its value at 0 is 1, therefore it's constant. It's the constant function 1 everywhere, the identity holds. Just like we proved sine squared plus cosine squared is 1. We could do that argument here. Anyway, so because that's true, this means that sinh squared of w is what? Looks like we got cosh squared w minus 1, right? But in the current context, that is z squared minus 1, right? Therefore, sinh w must be equal to what? Well, z squared minus 1 to the 1/2 power. Or if you like, I could write plus or minus the square root of z squared minus 1. Where I'm abusing a notation a bit, right? Because I'm talking about equality where I really should be saying an element of, to be fussy. Anyway, so what do we got? dw dz? Let's see here. Plus or minus 1 over the principal square root of z squared minus 1. There you go. Or, of course, you could also write this as 1 over z squared minus 1 to the 1/2 power if you just want to indicate it's a, So there's the derivative of inverse hyperbolic sine. I mean, inverse hyperbolic cosine. I can't remember where I started. Sorry. Yeah. Now, of course, you could also just do this, right? How about what's the derivative of the principal inverse? Let's see how this works together, right? Cosh inverse, big cosh inverse of z. Our explicit formula for that was what? d dz of what? We could use our formula. Big log of z plus the square root of z squared minus 1. And that gives us 1 over z plus the square root of z squared minus 1. But then you must multiply by the derivative of the inside function, which is what? 1 plus 2z divided by the square root of z squared minus 1. With a 2 down here, right? Because we're differentiating square root function. The derivative of the square root function is 1 over twice the square root function. Even here, that's still true. And so the 2's, they be canceling. What you got here? We'll make a common denominator here of, so the 2's cancel, and we've got 1 over z plus the square root of z squared minus 1, right? And then this I've got the square root of z squared minus 1 plus z divided by the square root of z squared minus 1. What do you know? Woohoo! And we're right back to where we got to a far less complicated way, as I showed you up above. Now, the advantage of the calculation on the bottom is it doesn't beg the question of the inverse function theorem. See, because that is just an algebra calculation, which I did. I found a stone cold formula for the inverse hyperbolic cosh, which we can differentiate, as we did. So whatever concerns you have, perhaps, about the inverse function theorem, you should set those aside, because I have an identity we can calculate. Yeah, which is probably why the book is doing it that way, because, you know, the inverse function theorem maybe is not known outside math. And this book is somewhat intended for engineers. It's actually really intended for engineers. This book is written by an engineer and a mathematician, which is why the section, like if you read the section on impedance, it's pretty good. You're electrical, right?
I'm non-mechanical.
Why are you in here? No, I didn't say that. No, we want all engineers of all kinds, all engineers. Bring them here. Tell them it's an easy course. There's no proofs, like hardly any proofs. And the calculations are just very simple. Very simple. You hardly need to remember anything from Calculus 3 at all, right? I mean, it's just, yeah. All right, I'll shut up. Anyway, so does that help with the inverse functions? Like, now there's a larger question that is kind of looming, which is the book talks about like selecting a branch of something. Like find a branch that works for certain context, and let me just find an example. The best thing is you should work an example. It's hard for me to describe the problem in general. Well, rats. Now's the time in the lecture where I feel like I'm forgetting something. I don't think I am. So this is the kind of topic that if I try to illustrate something and I get too ambitious in my example, things go very, very badly. Because it is not hard to ask a question about this issue, which is really, really subtle and annoying. But let me see if I can come up. Let me try to give a really easy example to start with. How about that? I'm going to aim for super easy. So example 4. So we're going to consider something like log of z plus 2. Select branch of this multiply valued function which is holomorphic, which is to say complex differentiable, right? On a set including let's say x plus iy such that x is less than minus 2 and y equal to 0. Okay, so as I think about this, I need to think basically about log, let's call it log sub alpha just to illustrate what's involved here. So if I pick the alpha branch of log of z plus 2, where's that? My question is like, where is this holomorphic? I think if we can answer that question, we can start to appreciate the examples I'm trying to give you. So where is this holomorphic? Like what's the problem with log sub alpha? Like where is it not holomorphic?
Everywhere where z plus 2 is not equal to the modulus of z plus 2 times e to the I alpha plus 2
E to the I alpha plus 2. Maybe I have to try to unpack what you just said. So here's the formula, right? So more to the point, like where is this discontinuous? Right. So I think what you're so Shane, I think what you're saying was if I said this is equal to like r e to the I theta, we cannot allow theta equals to alpha, right? That's the trouble. So because arg sub alpha, it's helpful to focus on the negative, like focus on the place where it breaks. So what I do to solve these kind of problems is I say, okay, I'm going to put z plus 2 equal to, well, r e to the I alpha, right? Because that's, you know, these are the, you know, this is what's forbidden, right? For logs of alpha z plus 2, that's the one thing I can't do. I can't have that equal to that, right? That's the problem. Those are the problem spots. And so what is that? So I've given you guys some problems on like graphing things and visualizing things in the complex plane. And I think generally speaking, you guys are really, really shaky on this stuff. And that's a problem because you can't crack these kinds of problems unless you understand what's polar coordinates, like, you know, have some kind of intuitive feel for what we're doing. Like if I write z is equal to minus 2 plus r e to the I alpha, can you tell me what that is? Can you graph it?
It's like a circle of radius r shifted over by 2 to the same right.
Maybe it's helpful. Instead of writing r here, let me prime the pump with a different letter, which we use in Calc 3, which is like t, right?
Oh, excuse me, that's a ray.
Yes. So isn't that weird? Like you changing the letter makes it like, oh, parametrization, right? This is a parametrization, like you said, of a ray that starts at minus 2, right? And then it goes out at angle alpha, whatever that is, right? You know, I'll choose alpha like that, just to. But you know, this is something out here is of the form t e to the I alpha, right? So you're, I'll just write it that way. I don't want to assume alpha is the standard angle, you know, but. So my question was, select a branch of this multiply valued function which is holomorphic on the set, including minus 2, y equals 0. So like my question basically just means what? The one thing we can't do is what? So the one thing I can't do to answer the question which I posed is I can't put it over here, right? That must avoid, right? Given my problem statement. So the one choice we can't make is the one choice that you guys will make if I don't have this conversation with you, right? Which is to just ignore the alpha sub issue and just say, oh, just use this, right? That is what you cannot do, because if I put just the standard logarithm, this is not holomorphic on the negative real axis. And the negative real axis thought for z plus 2 corresponds to the shifted negative real axis because there's a shift by 2. So like how many answers are to this question? Well, there's like infinitely many choices you could make, right? Like if I want a branch, I can select any branch I like. I can put alpha anything I want except for what?
2 by k.
Yep, exactly. So I think, nope. All alpha except alpha equal to, right idea, but shifted a bit, pi plus 2 pi. Well, I'll write it this way. And I'll say element of just because it's bothering me. See, remember the principal logarithm is basically alpha equal to pi. It's got the jump at plus or minus pi. And so like jump at pi, jump at 3 pi, jump at 5 pi. Any odd multiples of pi is the problem. Even's fine. Like for example, a positive solution here would just be this, like logo of z plus 2. This thing is holomorphic. So where is this? This thing is holomorphic everywhere except for, this is minus 2, right? It's got trouble over here. But this is, holomorphic on, you could say, I guess you could say this, minus 2 plus the positive slit plane. If you'd allow me that notation, if we can take a set and add minus 2 to it, what that does is it shifts the set to the right, to the left 2 units. So like this C plus, that's notation for the slit complex plane, but the slit is on the plus instead of the minus. This is C plus. So if I subtract 2 from that moves this thing over here like that. This is holomorphic everywhere except for that. And that would be a solution to the problem I asked here. There are infinitely many though. See, as long as I don't put the trouble spot, over where I've demanded I have it holomorphic, I'm fine. Yeah.
So when you say select a branch,
Yep.
would that be for little logs of alpha?
Yeah. Well, I'm not sure I have the notation for it, but like I have this log up here, it's in some sense equal to the set. I guess you could think of it like the set of log sub alpha of z plus 2, but I'm not sure that even entirely covers it, This much I can say, if you put w, here's probably a better way to describe it. If I put w equal to z plus 2, oh, I'm sorry, I'm trying to, just a second here, I'll get through it eventually. So if I have w equals log z, that means that z is what? Z is equal to e to the w, right? That's the meaning of w equals to log z. And so if I say this, I'm saying z plus 2 is equal to e to the w, right? Any solution to this is one of the little logs. The reason I'm saying it's not, the reason I'm being a little bit cagey is because the logs of alphas in some sense are maximal, but you see I could restrict the domain to be smaller and still have a solution to that. There's a lot of, and I also have the plus or minus thing. I could either include the alpha at the top or the bottom. There's a lot of subtleties there. Here, let's look at something less subtle. Like, let's figure out where is. So that wasn't the easiest. I tried for an easy example, but I think I failed. I mean, it's not that bad, I think. But what if we had f of z equal to the log of z cubed plus 1? You know, where is this holomorphic? And we're going to take the usual calculus approach of being as greedy as possible with the formula, right? All right, so what is the deal? Like, what is the problem? Our trouble is what? Troublesome case is z cubed plus 1 equals to minus t. Right? And I'm going to think of t being positive just for the sake of, you know, best results. Do you guys see why I say that? Does this make sense to you? The principal logarithm input, the one thing it can't be, is on the negative real axis. That's where you had the angle jump that you guys proved, sort of, in the last homework. You thought about proving. Yeah, okay. All right, so z cubed is what? Apparently minus 1 minus t, right? So how can you get that? You know? So this apparently means we're in trouble if we've got z is an element of like the third roots of 1 minus t, yeah? But what is 1 minus? Minus 1 minus t is a what? It is a real number, right? Now this, remember, we know how that works. This is the principal third root of minus 1 minus t, and then it's, you know, e to the 2 pi I over 3 times that, whatever that was, principal third root of minus 1 minus t, and then it's e to the 4 pi I over 3, principal root of the third root of minus 1 minus t. So can we calculate those? I mean, I hope we can. Let's start out with the, well, that's the thing that matters, right? The principal root of minus 1 minus t, what is that? So third root of 1 plus t in the real sense, right? That's the magnitude, I think. And what's the standard angle? Oopsie, I've been on the other board. So sorry, but you know, you're gonna fake being sick. You know, these things will happen. But sorry. Sorry. So we have e to the I pi over 3. Okay? Because the argument of minus 1 minus t is the argument of a negative number, a negative real number, and that is pi. The standard angle on the negative real axis is pi. Where do those come from? Well, those come apparently from anything of this form, right? And so we've got this one. And just for the sake of, I'm gonna say alpha equals the cube root of 1 plus t, just for the sake of, you know, writing this easier. And so what we got is we've got alpha e to the pi I over 3, right? And then what happens when you add, what's 2/3 plus 1/3? It's 1. What's e to the pi I?
Negative.
-1. So that's actually just minus alpha. See, because I have 2 pi over 3, and then pi over 3, which gives me a pi e to the pi I as -1. And then I get a minus alpha e to the pi I over 3, if you like. And what can you tell me about alpha? What can you tell me about alpha? It's greater than what? Greater than 1, right? Because t is positive, right? Not 0. So it's greater than 1. So if I graph this, if I dare, man, it is messed up. This example seems easier than the other one. I think, you know, I keep forgetting that when I ask you to select a branch from the infinity of choices, even the easiest example becomes subtle. Whereas if I give you a particular choice already and then ask you to analyze its properties, that is for whatever, well, for obvious reasons, much easier. Even though this is a much more complicated function than z plus 2, right? Z cubed plus 1 fed into the log is much worse, isn't it? So we've got 3 different things that are going on, right? Minus alpha would be like, so this is like the radius alpha circle. No, radius 1, radius 1. My bad. So this starts at -1 but not included, right? -1 not included, and then it keeps going and going and going. So I'm doing the middle one first, right, like that. This one starts at pi over 3, and then it goes on out like that. And this one is, did I do that right? 5 pi over, I know it, I'm almost certain it should be down here. So if I think I made a miscalculation somehow. Anyway, let me just get to the point. That's got to be a 5 pi over 3. I mean, if you do 4 plus pi over 3, you get 5 pi over 3, which is down here-ish, right? I don't know what I did in my head, but it was wrong. So that's not, so what I've just shown you, these are the trouble spots, right? So where is this function that we're looking at holomorphic? The answer is everywhere in the complex plane except for those 3 rays. And if you wanted to, well, anyway, that's what it is. So, and then if you were to do something like, instead of using log, principal log like we did, what if instead of that you tried to use like log sub 0? What would the difference be? Like, what if I changed this to log sub 0? Then I would look at, instead of putting minus t here, I would just put a plus t. And then I end up with like -1 plus t. And then it would be more complicated, you see? Because if you look at -1 plus t, what's the argument of that? What's arg sub 0 of that? We'll see if t is less than 1, I believe arg sub 0 would be, arg sub 0 goes from 0 to 2 pi, okay? So this would be pi if this was negative. But when t gets greater than 1, it becomes either 2 pi or 0, depending on what arg sub 0 was defined as. I think it was 0, if I remember right. Yeah, the sub 0 puts 0 in the choices, okay? Like I designed it so that arg sub alpha makes alpha the angle that it goes to if it's at that place. So like, essentially, so this is always a real number, right? It's either a negative real number or a positive real number. And so if that was the case, it doesn't quite work out the same, because the argument, arg sub 0 argument, it's either, you know, pi for negative inputs here, or it's 0 for the other. So I'd have to.
If t is 1.
Yeah, and if t is equal to 1, it's just not even defined. Yeah. Right. Exactly. So it is nastier. And that's what I find sometimes is when I've analyzed these things before, is you'll sometimes get it so like, you don't get like a ray, like some funky thing happens where the ray will get bent at some point or something. And so like the regions of holomorphicity can be more subtle than this. All right, anyway, so we're just asking the question, what's the domain of a function, basically, right? But now we have the logarithm to deal with, and this is what we're up against. So I hope those help you. There are some nice examples in the book that I have not done, but I'm going to shift over here to section 3.4 now. So section 3.4 is on washers, wedges, and walls. And I think you'll find that this part is like, well, I think it's considerably easier than what we've been doing up to this point today. No?
I read it and it made no sense.
You read it and it made no sense. Oh man. Well, I'm in trouble then, I guess. I don't know. So section 3.4, it's really just about solving Laplace's equation subject to certain boundary conditions. Do you guys know what a boundary condition is? Well, you know. Well, Shane has a certain advantage in that he's sitting in another class where we spend a whole day talking about boundary conditions, I guess. Although, well, anyway. So boundary condition is just conditions which hold on the boundary of some region. It is what it sounds like. And so, for instance, let's see here. What example am I on? 6. Here, let me start out. Maybe you want to solve Laplace's equation on the wedge below, and we'll do it like this. Let's see here. So, I don't know. Well, how about this one? All right, like this wedge here. So it goes on and on. We got theta equals to 0 down here, and we got standard angle pi over 4 up here, all right? And suppose I want to have, and this goes on and on, okay? So it's like an infinite pi. It's a sector, right? It just goes on and on. And for it to be a boundary value problem, I have to specify some values on the boundary, all right? So I want to have phi equal to 10 down here, and I want to make phi equals to let's say 20 up here. Okay? So the basic genius of this section is to notice that log of z is the natural log of the modulus of z plus, I times arg z, right? That what this means is that, and we worked this out, right? That the log of z and the argument of z are harmonic, right? They're solution to Laplace's equation. And so here's the genius, though, is to realize, well, we can just focus on either this or that. We'll just use argument here. So basically, here's a template. We just make a guess, an educated guess, that it can look something like some constant a plus some other constant b times. I think we can use principal argument here. Now that's what requires some thinking. Can we use principal argument here? If my z is from here, is principal argument okay?
What's phi?
Phi is the solution we're looking for.